This lecture deals with the analysis of trusses subject to uniformly distributed loads that move, like trains that move across a bridge. In the case of railroad bridges, the load could be considered uniformly distributed with a variable length, since trains that cross the bridge could have different number of cars. In this lecture, we are going to examine the maximum effect of such a load on three specific members in a truss bridge: a member along the top chord of the truss, a member along the bottom chord, and a diagonal member connecting the top chord to the bottom chord. We are going to determine the maximum compressive and tensile force in each member as a train moves across the bridge. The structure we are going to use in this lecture is a replica of an actual bridge which was recently constructed near Belgrade, Serbia. Given the nature of the structure, we know it's going to be subjected to loads of various lengths. It could be subjected to the weight of a single train car. And it should also be able to carry the weight associated with multiple cars covering the entire length of the bridge. In this analysis, we consider the weight of the train to be uniformly distributed over its entire length. Given the symmetrical nature of the bridge and the load, we only need to consider one of the trusses. Here, we assume the bridge is pin-connected at the left end and rests on a roller at the right end. Knowing the dimensions of the truss, we are now ready to perform the required analysis. Although we don't need to have section and material properties of the truss members for our purposes in this lecture, they would be needed for calculating joint displacements and member stresses when designing the bridge. Let's start by making an important observation. Regardless of the position and length of the distributed load applied to the bridge, the top chord of the truss will always be in compression, while the bottom chord will be in tension. But the inclined member could either be in compression or tension depending on the position of the load. As you are going to see in a minute, that means in order to determine the maximum compressive force in this member and maximum tension force in this member, the distributed load needs to span the entire length of the bridge, whereas the maximum tensile and compressive force in the inclined member develops only when the bridge is partially loaded, when the load is either toward the right end or the left end of the bridge. In order to determine the maximum axial force in each of the three members, we start by drawing their influence lines. This involves placing a unit load at each of the joints along the bottom chord of the truss where the railroad track rests, then calculating the axial force in each member due to that load. When the unit load is placed at the first inner joint from the right end of the truss, we end up with these support reactions. Since we are interested in calculating axial force in members AC, BC, and BD, we can cut the truss like this, dividing it into two substructures. We can then use either of the two free body diagrams to determine the three unknown member forces. Note that here we have assumed all three members to be in tension. But before we start writing the equilibrium equations, we need to determine the inclination angle of member BC. The angle, approximately, is 72 degrees. We need three equilibrium equations in order to determine the unknowns. Since FBC is the only unknown force with a component along the y-axis, if we sum the forces in the y direction, we get. Then, writing the sum of the moments about joint B, we can determine FAC. Finally, summing the moments about joint C yields FBD. We have one member in tension and two members in compression. Let's start graphing the three influence lines. Since BD is in tension, the value is plotted above the x-axis. In the case of BC and AC, the values appear below the x-axis since both members are in compression. Moving the unit load to the next joint, we get these support reactions. And if we cut through the three members again, we get this free body diagram. Using the same scheme as the previous step, we can determine the three unknown forces. Updating the influence lines, we continue moving the unit load along the bottom joints. In each step, we determine the support reactions, then cut the truss, write the equilibrium equations, and determine the unknown forces before updating the influence lines. Note the switch in the sign of the axial force in member BC when the load reaches joint B. The member goes from compression into tension. This shift is reflected in the influence line by a jump in value from negative 0.421 to positive 0.526. We continue moving the unit load and populating the influence lines until the unit load reaches the left end of the truss. Here are the three influence lines. We are now ready to determine the maximum effect of the distributed train load on each member. Suppose the bridge is expected to carry train cars with maximum load of 40 kilonewtons per meter, and the smallest car would have a length of 12 meters. Given that each of the two side trusses carries half of the total load, then our uniformly distributed load for each truss is going to be 20 kilonewtons per meter. The length of the load could vary from 12 meters to 55 meters, which is the total length of the bridge. Member BD, situated along the bottom chord of the truss, is always in tension. That is why the influence line for the member appears above the x-axis. The diagram shows the various force magnitudes in the member based on the location of a unit load. For example, if a load of 1 kilonewton is placed at this joint, then a force of 1.068 kilonewton develops in BD, and if the load is placed here, the force in the member increases to 1.164 kilonewton. If we place the two unit loads on the truss at the same time, then the total tension force in BD becomes the sum of 1.068 and 1.164. What would be the tension force in the member if we place a uniformly distributed load of magnitude 1 on the entire truss? In such a case, the total tension in the member equals to the sum of all the values that the influence line represents. That is, the force equal to the total area under the influence line. So, for a uniformly distributed load of 20 kilonewtons per meter, the total tensile force in the member can be calculated this way. Note that this is the maximum tensile force that could develop in the member, which takes place when the train covers the entire span of the bridge. Since the influence line does not have any negative area, no compressive force develops in member BD, regardless of the position and length of the load. The influence line for the inclined member BC has a positive area and a negative area. When the distributed load is over the entire positive area, maximum tensile force develops in the member. When the load is over the negative area, the member undergoes its maximum compressive force. To determine the positive area, we need to calculate this distance, which requires determining this smaller distance. Note that here we have two similar triangles. We can use the base to height ratios to determine distance x, which enables us to calculate the total base of the positive area. Now we can calculate the total positive area under the influence line. This gives us a maximum tensile force of 161 kilonewtons in the member. And when the distributed load is over the negative area of the influence line, we end up with a compressive force of 103 kilonewtons. For member AC, since its influence line has no positive region, we place the distributed load over the entire length of the truss in order to determine the maximum compressive force. It equals 890 kilonewtons. No tensile force develops in AC. To summarize, when the train is over the bridge covering the rightmost 24.44 meters of the track, member BC experiences its maximum compressive force. When the entire track is covered, both AC and BD undergo their maximum axial force. And when the train is over the leftmost 30.56 meters of the track, the maximum tensile force develops in BC. We can determine the effect of the moving load on the other truss members in a similar manner.